All right, so the last thing we're doing in 6.1 is using some identities, possibly using some identities to solve trig equations. So ultimately, when we test over chapter 6, it'll be 6.1 through 6.4, and that's not going to be for a good while because your third test is going to be final exam review. I'll sit in the back today so you don't have to awkwardly look at me because I get it. I get it. Huh? I don't know if I want to get used to it or y'all to either. So you're going to have the first section, which you're going to be solving, I think, 4 out of 5 proofs. The middle section is solving equations, and the last section is solving 3 out of 4 proofs using the identities from 6, 2, 3, and 4. So this is essentially going to be the middle section, solving equations, okay? So when we solve equations, remember what type of equation is it from this category up here? Conditional, yeah. So we're trying to find the conditions under which the equation is true. So let's take a look at example 7. Find the solutions. Okay, got it. I know the instructions. That means solve for this equation here, such that, and there's multiple parts. The solutions are between 0 and 2 pi. That's our comfort window, right? 0 and 4 pi, so that's going to be all the ones from 0 to 2 pi plus another rotation. And then all of them for all real numbers. Yikes, from negative infinity to infinity. Okay, so what do you notice about this equation? There's two variable terms. One of them is sine squared and one of them is sine of x. Now, let's kind of go back and think about when the last time we saw something like that that had a squared term and a non-squared term.
Good morning, unicorns. Teachers, pardon this interruption. Just a reminder that Texas State University will be here today at 10:45 a.m. Please sign up and get your passes in the College and Career Center. Thank you.
Last time we saw something with a squared variable and a non-squared variable, it was something like that, 2x squared plus x plus 1. How would we go about solving something like that? If it were, what's that? Would we pull out an x right now while it's equal to 1? That would be to try to factor the left side. Right, we got to set it equal to 0, because if I factored the left side, it wouldn't be wrong, but I couldn't set each factor equal to 1. That only works when it's 0. So we would have to get everything on one side. So that would be 2x squared plus x minus 1 equals 0. And now when it's equal to 0, then we could factor it. So then we would look for, target sum, target product. The leading term is 2x squared, so it's got to be a 2x and a 1x. The last term is a 1, so it's got to be a 1 and a 1 because it's prime. Now we just make sure the sign works. The middle term has to be positive, so the larger sum has to be positive. So it should look like that, right? Yes? And then from there, we would say 2x minus 1 equals 0, or x plus 1 equals 0, and then we would solve for x, right? We get x equals 1/2, or x equals negative 1. Well, guess what? We're going to do the exact same thing for something like this, except instead of x, guess what our x is going to be? X up, yeah, good. X up here was the non-squared term. That's going to be sine of x. Okay, so let's just kind of go through it so you can see the work. It's going to be 2 sine squared of x plus sine of x minus 1 equals 0. And now we're going to factor it. The squared term is sine squared. The linear term, the non-squared term, is sine of x. So that's going to factor times 2 sine of x minus 1 times sine of x plus 1. So we could factor quadratics if it's more than just plain old x. And here's kind of the illustration, right? Now, if you FOIL that out, you can see that it actually works. 2 sine of x times sine of x is sine squared of x. Sine times sine is sine squared. All right, so then we would set each of those equal to 0. 2 sine of x minus 1 equals 0, or sine of x plus 1 equals 0. Just like over there. And now we would solve for not x just yet, but sine of x. So sine of x would equal 1/2, or sine of x would equal negative 1. Now, when we hit that mark over here, we were done because we had already solved for x. When we do that over here, we're not quite done, okay? We've solved for sine of x, which is a really important thing to do, but we haven't solved for x. So now we solve for x. And the way we solve for x is by looking at our watch and realizing that it's unit circle time, everybody. Unit circle time. So part A, from 0 to 2 pi, within one positive resolution, where is sine equal to a half? We're not looking for the inverse sine function now. We want all the solutions between 0 and 2 pi. So where is sine equal to positive 1/2? Pi 6, that would be the one in the PVR. 5 pi 6, good, in quadrant 2. We want all the solutions. Okay, so both of those are the solutions. That's it for that one. And then coming over here, where is sine equal to -1 within one rotation? There's only one place, right? 3 pi halves, good. And we call it 3 pi halves, not negative pi halves, because we're not in the PVR. We're once around the positive rotation. So that's part A. So there's just one more step to go than if it were just plain old x. Okay, so you need to train yourself to see that when we start. Squared term, non-squared term, constant. Okay, well part B just says now from 0 to 4 pi. So that's just going to be one more full rotation. So it should be all of the ones we have above, pi 6, 5 pi 6, and 3 pi halves. And then we should go around one more cycle, right? Which means the next 3 we want are going to be what with those 3? Coterminal. Good. So all we have to do is add a full rotation to those. So if we add a full rotation to pi 6, what do we get? Is a full rotation 1 pi or 2 pi? 2 pi. So remember, that's twice the denominator. So one rotation, in this case, for pi 6 is going to be 12 pi 6, right? So 12 plus 1 is 13 pi 6. Add 12 to 5 and get 17 pi 6. And then 3 pi halves, we add a full rotation, which gives us what? Now full rotation is still 2 pi, but it's 4 pi halves. So 4 plus 3 is 7 pi halves. All right, bless you. So we went around twice. We had the first 3, and then the next rotation gave us the next 3. Those are coterminal. All right, and we could do that for any interval, but part C says now do it for all real numbers. Oh my goodness. Well, how many solutions are there going to be from negative infinity to infinity? Infinitely many. It's going to be physically impossible to list them all. So what we do is like what we did when we were listing domains with vertical asymptotes. We're going to find our favorite one and then just say how often they occur. Well, our favorite solutions are probably the ones within one rotation that we did on part A. So let's go ahead and do that. We're going to get x equals pi 6 plus multiples of what to get coterminal with that one? How do we get 13 pi 6? Yeah, plus 12 pi 6, or you could say just 2 pi n. You don't have to give it a nice denominator. Whoever wants to generate them can do that. Plus 2 pi n, where n is an integer. So that gives you all of the ones associated with that one. Then we do it for the other one. We get 5 pi 6 plus all of his coterminal buddies. And then the other one, 3 pi halves plus his coterminal entourage. There we go. So that's how you do it for all solutions. And then whoever wants to can come in there and add or subtract multiples of 2 pi to generate the ones they want. Okay, so that's solving the trig equation. It's a little more fun than just solving a polynomial equation because we get to use the unit circle. Yay. All right, any comments or questions on that one? Not bad for a Monday morning. Kind of a good way to start out spring fling week. What are y'all looking forward to most? Monday through Friday or Monday through Thursday? or Friday? Okay, Monday through Thursday. Good. All right. Good answer. Good answer. Yeah. All right. Example 8. Find the solutions. Okay, so it's a conditional equation again. This time we got cosine cubed over sine of x times cotangent of x, such that x is between negative 2 pi and 2 pi. Okay, this one says to be careful not to lose any variable informations while you are solving. What the heck does that mean? Okay, well, let's see. It's a conditional equation. Now, notice for the first time here, I have a denominator. So whenever we have denominators, remember, we can't divide by 0. So whenever sine of x is 0, namely at 0, pi, 2 pi, 3 pi, those are not going to be solutions. Okay? You also want to be careful, like it says, when you're in the process of solving, not to lose any variable information from both sides of the equation. Because when you do that, you lose potential solutions. Okay, what do I mean by that? If I had like x cubed equals x and I ask you to solve, you don't want to divide both sides by x and say x squared equals 0, therefore x equals 0. Why? Because I lost an x from both sides and I lose potential roots, right? Are there any other values that work besides 0? Well, let's see. What I should have done is bring everything across and set it equal to 0. And now instead of dividing it out and getting rid of it, I'll divide it out, but I'll factor it out and leave it visible. And now when you set them both equal to 0, you get 0 or negative 1 or positive 1. Oh, yikes. I lost 2 whole solutions by doing it this way. Okay? So you don't want to do that. Don't lose information from both sides at the same time. If it goes away from one side but reappears on the other side, that's okay. But if it goes away from both sides and it's a variable, that's bad. Bad. Like Michael Jackson was back in the day. Yeah, he's saying about being bad, like bad A, but now we're finding out with the Netflix, that he was bad, like with children bad, which everyone kind of suspected. Man, why did that come up? All right. Okay, so what to do? Good question. Good question. Well, what we did on the previous one is we got everything on one side and set it equal to 0, which is not a bad thing to do. If you ever have more than one variable term, get everything on one side and set it equal to 0. So let's do that. So cosine cubed of x over sine of x minus cotangent of x. And now it's equal to 0. Cool. And so now you look for common factors. Do we have any other common factors besides CO? No, and that doesn't even make sense. So, I'm kind of stuck. I wish I can kind of make them look more like each other, right? Yes, here's where we're going to use identities. We didn't do that on the first one. We didn't need identities, but here's where identities are useful. Yeah, put everything in terms of sine and cosine is still a good thing if you're solving equations. What is cotangent? Cosine over sine. Good. And now you're like, yay, I have a common denominator. So let's get a common denominator. So it's cosine cubed minus cosine all over sine of x. Now this is how you want to solve equations that have variables in them, or with fractions. You want to get everything on one side and get a single fraction. Okay, now, when is a fraction equal to 0? When which part's 0? Yes, when the numerator equals 0. This is how you avoid getting solutions that give you division by 0. A fraction equals 0 when the numerator is equal to 0. So now all you got to do is set the numerator equal to 0. Now notice what we're not doing. I am not multiplying both sides times sine. I'm not doing that. If I did, it would divide out on the left, and 0 times sine would be 0. I would end up with this line that I'm currently at. But that's not how I'm getting to that line. I'm keeping this preserved like this because I want to remember that sine can't be 0 because I'm dividing by 0 then. But instead, I'm just setting the numerator equal to 0, okay? So it's going to give you the same result, but by a slightly different reason. All right, so now, yay, 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 yay. Look for a common factor. We have one. So I factor out a cosine of x, and I'm left with cosine squared of x minus 1 equals 0. And now, since they're factored and they're equal to 0, I could set each of them equal to 0. So cosine equals 0, or cosine squared of x minus 1 equals 0. Now, we'd be pretty much done if this were just x's, but it's not. They're trig functions. So on the left, we're ready to go. It's unit circle time. So where is cosine equal to 0? Now, remember what our interval was? Negative 2 pi to 2 pi. So I can find all the ones from 0 to 2 pi, like I'm used to. And then how do I get the ones from negative 2 pi to 0? Subtract the full rotation. Yeah, I'll subtract the full rotation. All right, so where is cosine equal to 0 in our wheelhouse from 0 to 2 pi? Pi halves and 3 pi halves. Good, on the y-axis. So then all I have to do is subtract a full rotation from both of those to get the other ones that are coterminal. So full rotation is 2 pi or 4 pi halves. So what's pi minus 4 pi? Negative 3 pi halves. And 3 pi halves minus 4 pi halves is negative pi halves. So those are the 4 associated with that one. And now I go over to the other side. And I got to solve for cosine of x. So I get cosine squared of x equals 1. If I take the square root of both sides, which I can, because this is a conditional equation, what do I have to remember to do when I take the square root? Plus or minus, yeah. So that's going to be plus or minus 1. Which if you didn't remember the minus, you're going to lose 2 of your solutions. So where between 0 and 2 pi is cosine either 1 or negative 1? At 0, 0, and at pi, right? Now notice that our endpoints right here are brackets around both of them, right? So we can go all the way up to 2 pi. So 0, pi, and 2 pi. And now I'll subtract a full rotation. 0 minus 2 pi is negative 2 pi. Pi minus 2 pi is negative pi. And 2 pi minus 2 pi is 0, which I already have. So basically that one's hitting all of them here at 0, pi, 2 pi, and then going back around negative pi, negative 2 pi. So how many solutions does this fella have? 4 over here and 5 over here, so 9 total solutions from negative 2 pi to 2 pi. Okay, now we do want to check one thing. Remember, sine can't be 0. When is sine equal to 0? Sine equals 0 when x is 0, pi, 2 pi, so on and so forth. Uh-oh. What's the sine value at those last 5? 0. Can I use them? No. These are not in the domain. Okay, they're off limits because we started with originally. You always have to go back to what you originally had, and sine can't be 0 because we can't divide by 0. All right, so they're kind of extraneous solutions, but you got to make sure you check. So whenever you have a denominator, be very, very aware of what could possibly happen. Okay, and that's why we preserve it all the way through. We still have it here. We only set the numerator equal to 0. Okay. Why can't you? Oh, from this little thing right here. We're going to start by finding the zeros of the function by seeing when the numerator is 0, because 0 divided by 2 equals 0, 0 divided by negative 10 equals 0. So a fraction is equal to 0 when the numerator is 0. Once I find those values, though, I just have to come back and see, do they make the denominator 0 as well, because I can't have that. And then you throw out the ones that do. Okay? It's like finding the domain of a function. Okay, so that one had a little bit more to it. And that's not the only way to do it, because you could have put it in terms of cotangent, but that's probably the best way to do it. All right, I want you to go ahead and do number 9 on your own. It says to find all the solutions. So let's just talk real quickly about what your strategy is going to be. All of them means from negative infinity to infinity. So how do we do that before? Yeah, find all of the ones from 0 to 2 pi, and then for all of those solutions, say plus 2 pi n. Okay, and that'll get you all of them. Kinda. I mean, your goal is still the same, right? You have two terms that have trig functions in them. So your goal is to get everything on one side and set it equal to 0. If you only have one trig term, like notice right here, we only have one trig term in that equation. So that's when you want to isolate your trig term. Okay, get it by itself and get everything on the other side. But if you have more than one term that has trig in it or variables in it, and we have two terms, get everything on one side and set it equal to 0. Factor and then set them both equal to 0. Okay, so now go ahead. Terms. The one on the right is a term, so when you bring it across, it just becomes minus. So notice you do not want to divide both sides by tangent, because then you'll get rid of the tangent factor from both sides. So you subtract it from both sides. You somehow got it squared right there. Yeah, it's just going to be minus tangent. So some of y'all already have the factor step factor step done, sorry, which is good, by factoring out the common factor, which is the first rule of factoring. Once you subtract the tangent, you get minus tangent on the left equals 0, and there is a tangent factor that is common in both. So we'll factor the tangent out, and we're left with the square root of 2 cosine of x, and then minus, remember if you have two terms to start with, you're going to have two terms to end with. Factoring out is dividing out, and tangent divided by itself is 1. So once you have it set equal to 0 and factored, you're kind of home free. Now you set them each equal to 0. So tangent of x equals 0, or square root of 2 cosine x minus 1 equals 0. And now it's everybody's favorite time, spring fling and unit circle time. So it says to find all the solutions, but we have our strategy. We're going to find the ones within one rotation. So where is tangent equal to 0? Yes. Where y equals 0 or where sine equals 0, right? So 0, pi, and yeah, very good. We don't need to go to 2 pi because it's coterminal with 0. So let's just, instead of do it like that, we'll say this, and we'll say plus 2 pi n plus 2 pi n, where n is an integer. Now notice in this case, you can actually write that as a single equation because they actually occur a half rotation away from each other. You can condense it down. Normally you can't do that because they occur in adjacent quadrants, and you can't go to one and then go around to the other because they're not spaced evenly. But these are spaced evenly apart, right? So if you wanted to, you could just pick one of those and go multiples of what? What if I wanted to start at 0 and then hit the next one? I wouldn't go all around 2 pi. I would just go to pi, right? And then add another pi. And then add another pi. So I could just say x equals 0, which is 0. I could just say pi n, where n is an integer. Okay, you can't always get it down to a single one. In general, if you take the 2 that you're given and just say plus 2 pi n, it's going to work. But sometimes if they land on the quadrants on opposite sides from each other, you could do it like that. All right, now this one, you solve for cosine of x this time because there's only one variable term. That's when you want to isolate the variable terms instead of keeping it equal to 0. That's going to give you positive 1 over the square root of 2, which when you rationalize that gives you square root of 2 over 2. And now you should recognize that ratio. Where is cosine equal to square root of 2 over 2? Pi fourths, and cosine is positive when x is positive, quadrant 1 and quadrant 4, so that's 7 pi fourths, yeah, plus 2 pi n. And again, notice here you cannot write that as a single equation because one's there and the other's here. And there's no way to go from this one to here and then go a different distance to there and then to there. They're not spaced halfway around from each other. Okay, so you have to list those as 2. So there you go. These 2 here and the one I boxed, or that one, those 2 there and these 2 over here. Either one, okay, are your solutions. All right, having a good time? Sweet. All right, let's take a look at this one. It says find all solutions again. So same strategy, find the ones between 0 and 2 pi, add 2 pi n. Such that, and I think I used that the other day, that's the pitchfork variable. Any future psychologists in here? Psychologists have Kilford? Yeah? Do you recognize this symbol from psychology? Oh, you haven't? This is the symbol for the like National Bless You Psychology Institute. Bless you, bless you, or the psycho. No, not lambda. What does psychology start with? What sound? Psi. Good. Okay, but it's psi, like pounds per square inch. It's psi. All right, now this one's from -4 pi to 0. So this one's kind of weird. This one is within one negative rotation and then another negative rotation. So two negative rotations. So what we could do is find the ones that we are comfortable with from 0 to 2 pi and then subtract the full rotation twice to get the ones we want. Okay? It's always easier if you work through the ones you're comfortable with. And then breathe a sigh, really. Okay. If you don't like psi, call it X, okay? In fact, I'll do that. If you want to do that, you can. Call them X. I don't like you, psi, and you cross them out. Or white them out, yeah. Now, what should be our first step here, since we have at least two variable terms? Get everything on one side. Again, that's kind of been the common thing. If you have more than one term with variables, get it equal to 0. If you have only one variable term, isolate it. Get everything on the other side. So we get 3 sine of x minus 2 cosine squared of x equals 0. And now you look for a common factor, and you're like, ooh, I see 1. Common factor of 1 or -1. That's not going to be real helpful. And you can't factor out the x, remember. No. That's sacred. That's on the inside. That's part of the angle. Shoot. Easy. I need to somehow change something so that I have something in common. Any ideas? This is where your identities might be helpful, right? Because that helps us change the look equivalently. To get a common denominator, to get a common factor, I'm going to need either a sine in both terms or a cosine in both terms. So what are our options? I can either write sine in terms of cosine or cosine squared in terms of sine. Which one's easier? There's an identity that puts sine in terms of cosine? Sine is 1 over cosecant. Oh, yeah, sine over cosine is tangent. So sine would be tangent times cosine, but I don't want to bring a tangent into here. Can we write cosine squared in terms of sine a little bit easier? Yes, a la what? By way of, when you have a squared trig function? Papa, kid. Good. So put it in parentheses. Put it in parentheses first, because we're going to replace cosine squared with what it's equal to in terms of sine squared, which is what? If 1 minus sine squared. You'll get real used to that. Good. And sine squared is 1 minus cosine squared. Yay! Now it's partially factored, so we will distribute. So we get 3 sine of x minus 2 plus 2, bless you, sine squared of x equals 0. So now I have two terms with sine in it, but now that constant, that stupid constant, ruins the common factor for me. But what do you notice? I have a squared term, a non-squared term, and a constant. And have we seen that already today? Yeah, that was the one we started with up here. That could be a factorable quadratic in terms of sine. So let's go ahead and write it in descending order. 2 sine squared of x plus 3 sine of x minus 2 equals 0. Now, if your leading term happened to be negative at this point, which sometimes it might be, like a -2 sine squared, just multiply both sides by -1. Distribute it. Change all the signs. Okay? Real easy. We like factoring when the leading coefficient is positive. All right, now 2 is prime, so it's got to be a 2 sine of x and a 1 sine of x. And then 2 is prime, so it's got to be either a 2, 1 or a 1, 2. You could do trial and error. You could split the middle term. We've already learned how to factor it. The 2 times 2 is going to give you a 4. It should be positive because the middle term is 3. And on the inside, it should be a minus sine of x. So that should do it. If you want to FOIL it back out and verify, you'll see that you get the right answer. So everyone okay with the factoring part? If you need to go off to the side and write it as 2x squared plus 3x minus 2 first and factor it, I guess that's okay, right? And then come back and replace x with sine of x. So now we set them each equal to 0. So 2 sine of x minus 1 equals 0, or sine of x plus 2 equals 0. And now, because there's only a single trig or a single variable term, we isolate it. We get it by itself. So sine of x is a half, or sine of x is negative 2. And now it is once again a unit of circle time. Unit circle time. So where between 0 and 2 pi is x equal to positive 1/2? Pi 6 and 5 pi 6. Good. Now those aren't our final answers. So remember, we wanted them between negative 4 pi and 0. So I need to subtract 2 full rotations from each of those. So what's pi 6 minus 2 pi? Or in this case, a good version of 2 pi to use, as we've already seen, is 12 pi 6. So what's 1 pi minus 12? Negative 11 pi 6. And we got to do it one more time. Negative 11 minus 12. Negative 23 pi 6. And now I'm going to cross out the pi 6 because I don't need it. Because I'm only looking from negative 4 pi to 0, which is 2 full negative rotations. Now I'll do the same with 5 pi 6. 5 minus 12 is negative 7 pi 6. And then negative 7 minus 12 is negative 19 pi 6. And then I'll get rid of the 5 pi 6. Okay, see how we did that? Find the one in our wheelhouse, and then, okay, go back 2 rotations, get rid of it. All right, and now the last one over here, we still have the second branch to go down. Where does sine of x equal negative 2? For what angle x does sine equal negative 2? Let's see. Well, it would be below the y-axis, but sine equaling negative 2? Negative 2? Good. Is 2, negative 2, a legal sign ratio? Sine has to be between negative 1 and 1. So yes, good. This is no solution. All right, no solution. And so the 4 solutions that we have listed are the only 4. Yay! Math is fun! As I yawn and stretch at the same time. It's not easy being the rock. Ugh. Oh my gosh, look at example 11, rapid fire. Mixed practice. Okay, let's see if we can do maybe some of these. If we don't finish today, we don't finish today. Is that okay? I mean, who wants to rush through this stuff? No. Savor the flavor, right? It's like you go to McDonald's and you get a Big Mac. You don't want to just scarf that thing. Bless you. You want to take small bites and just savor every bite of Thousand Island dressing in there, right? Because it's delicious food. You just want to savor the flavor. Maybe not at McDonald's. That's just what came to mind. I don't know. Myron Steakhouse, maybe, right? A steak or something. Yeah. Okay. It's already equal to 0. How many variable terms do we have? Just 1. So in this case, we really don't want it equal to 0, right? If you only have 1 variable term, your goal is to isolate it. So there's nothing common to factor out, so we just get 2 sine of x then equals negative square root of 3, and we divide through by 2, and we get negative square root of 3 over 2. And now it's everybody's favorite time. By the way, we're going to find all of them between 0 and 2 pi. Okay, that's our wheelhouse. So now, where is sine equal to negative square root of 3 halves? Is it a pi 6 or pi thirds reference angle? It's a pi thirds reference angle, and they're both below the x-axis. So quadrant 3 and 4, 4 pi thirds and 5 pi thirds, right? There you go. There you go. We're done. That's it. Easy. Fun easy. It's fun. It's easy. It is fun easy. Fun easy. Fun easy. Trig equations. All right. 4 secant squared of x equals 8. What do you want to do? Bring it across and set it equal to 0. Isolate. Isolate because there's only one variable term. So divide through by 4. 8 divided by 4 is 2. Take the square root of both sides. And you get secant of x equals plus or minus the square root of 2. No, now do y'all remember secant used to be, square root of 2 used to be a secant ratio? Remember that? Here's a little tip. Are you more comfortable thinking in terms of secant or cosine? Cosine, I am too. If the secant ratio is the square root of 2, what would the cosine ratio be? 1 over the square root of 2. Muy bien bien. You could do that. It's like using the reciprocal identity, flipping both sides. If you know the cosine ratio, call it or if you have the secant ratio, flip the ratio and call it the cosine ratio. And now that's easier for us because 1 over the square root of 2 is really square root of 2 over 2. So you don't have to. You could remember where secant was square root of 2, but it's just a little bit easier if you write it in terms of sine or cosine. So now what is the reference angle when cosine is square root of 2 over 2? Pi fourths. And because we want it to be plus or minus, it's all of them. So let's just walk around the circle. Pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. Yeah. It's positive at 2 of those and negative at the other 2. If you forgot the negative when you did plus or minus, you left off 2 of the 4 solutions. Yeah. On the test, these are, thank you for calling me Corpy. On the test, these are going to be worth 2 checks apiece. So if you forgot the plus or minus, you'll get 1 check for doing the correct procedure, but you're not going to get that second check for finishing with all the 4 solutions, okay? And missing a check here or there, that can really add up, right? Pretty soon you're missing all the checks and you're still passing with like a 45. How does that work? How does that work? Yeah. Right. No, not 45 wouldn't be passing. Maybe about 56%. Yeah. Yeah. We don't want to lower the bar too much, right? Unless you're playing limbo, right? And then it's how low can you go? All right, let's call this the last one, okay? Last one. It's equal to 0, but is that how we want it? No, there's only one variable term, so let's isolate it. So 4 cosine squared of x equals 3. Divide through by 4, and you get 3/4. And then you take the square root, and you do plus or minus the square root of 3/4. Oh my gosh, is the square root of 3/4 a unit circle ratio? Not immediately recognizable as one, but remember, we could take the square root of the top and the bottom separately. So that's going to be the square root of 3 over the square root of 4. What is the square root of 4? 2. OMG. Is that a meme, OMG? No. Okay, square root of 3 halves. Oh, it was a unit circle ratio, just in disguise. Dressed as a meme. I don't know what a meme is. That's a unit circle ratio. So it's plus or minus. So what's the reference angle where cosine is square root of 3 halves? Pi 6. And now we want all of them. So let's again walk around the unit circle. Pi 6, quadrant 1. Quadrant 2 is 5 pi 6. Good. Quadrant 3 is 7 pi 6. And quadrant 4 is 11 pi 6. It's positive at 2 of those, pi 6 and 11 pi 6. and it's negative at the other two. Again, notice if you forgot the plus or minus, you wouldn't get half of the solutions. So they're fun, they're easy, they are fun easy. So we'll finish pretty easily tomorrow. We'll roll right into the next section. We'll probably quiz on Wednesday. Okay? Yay! I love Wednesday quizzes. You're welcome.